Okay, so let's do electrochemical cells, and I think that's pretty much going to be it. There's one brief thing on the Nernst equation in the end, but let's talk about electrochemical cells. There are two types of cells, a voltaic and electrolytic cells. So a voltaic cell or a galvanic, this is a battery. This is what you know well, this is a battery. Okay, this is going to give us energy. I plug this in, it provides electricity because this is a spontaneous reaction. Okay, delta G is less than zero, it's negative. Therefore, it's going to give us energy out. It's going to immediately start to go. The electrolytic cell, and we're going to see like one of these, electroplating. If I want to coat something in an electro and basically in some kind of metal, I would use an electrolytic cell. Very big difference is, again, this is a positive delta G. It is non-spontaneous. I have to put energy in, but we're going to focus on the voltaic cell pretty much exclusively. Okay. So the big thing here is the delta G is negative. So this is what you're used to seeing. An anode and a cathode, you have this electrolyte, you have this little salt bridge in between the two, and electrons go between the anode and the cathode. So a couple of things. So first of all, another mnemonic for this: oxidation occurs at the anode, electrons are lost, oxidation is lost. Reduction occurs at the cathode, electrons are gained. An ox and a red cat. An ox and a red cat. Hopefully this burns that into your memory. An ox and a red cat. Anode, oxidation, reduction, cathode. And you can think about that in terms of charge. So here we have a half reaction at both locations. Again, we see zinc solid turning into zinc 2+. We know that this is occurring because, again, an oxidation is occurring. So this zinc is going into solution. Okay, it's giving up its electrons. Where are its electrons going? Its electrons are traveling through this wire to the copper. And what we see is a red cat. This is the cathode. And so what you see here are copper 2+ turning into copper solid. Okay, and again, we're seeing that because the two electrons, if we're to balance this out, those two electrons are gained from the other side, and the copper ions are going in that direction. And so over time, what we see is this change where we lose that anode and we gain that cathode because of the transfer. Now, it's important to say, why is the salt bridge there? Well, it completes the circuit. Well, how does it complete the circuit? Well, if I am putting 2+ ions into solution, I need to add some charge compensation. If I didn't have the salt bridge there, this is not going to function, because very quickly, this whole thing would become positively charged, and it would just not happen because positives don't want to stay positive, right? We want to neutralize things. So that's why the salt bridge is here, is to put ions in solution to take care of the ions that are being gained to that solution. Much like this, we're losing copper 2+, therefore we're losing 2+, then it's becoming negative, and we're using this whole thing becoming negative. We need to drop some sodium ions in order to compensate for the thing that we are losing. Okay, so an ox and a red cat, we have both of these things that we just wrote out occurring at opposite anodes and the anode and cathode. So quick notation for this. So we see this right here as a phase barrier. And this would be my salt bridge. And the best way to think about it is left to right. These are the arrows that are occurring, right? So we have zinc turning into zinc 2+ and copper 2+ turning into copper solid. And that's it. I just want to skip through this next part, mostly just because I want to get through this relatively quickly and look at the practical stuff. This works because the reactions together are a negative delta G. So we see this as overall, we see this as a spontaneous process. Why does this work, or how does this work? Well, if I have an anode and a cathode, an anode and a cathode, and I have electrons in between the two of them, without getting too technical about this stuff, electrons get repelled from the negative, get pulled toward the positive. And again, we have that little salt bridge that connects those two. Right. So it's kind of the electrons are transferred because of the positive and negative. And that's terrible. Let me get rid of this thing. Terrible salt bridge. Here's my salt bridge. Okay. All right. So in terms of units, we're going to see a couple of units that are important. Volts, because we're going to talk about voltage and volts. Volts, V. 1 volt is equal to a joule per coulomb. Well, we know what a joule is, but we don't know what a coulomb is. So let's talk about a coulomb. Coulomb is a unit of charge. So the Faraday constant, which you're given, is equal to 96,485 coulombs per mole of electrons. So for every mole of electrons, we have 96,485 coulombs that are transferred. And you can look up the individual charge. In fact, we can calculate it from this, the individual charge of 1 electron, but we're usually talking about moles of electrons. So if you look at any of these reactions, right here, I see I'm transferring 2 electrons, but really what that is it's moles. So I'm transferring 2 moles of electrons. And notice that that would cancel in this case, right? So 2 moles of electrons. So N is equal to 2 in this case. And we're gonna run into that. So the moles of electrons, this whole thing here is the thing that is transferred within the reaction. This is going to be equal to N. So we're gonna see that at the very end here. N is equal to 2 moles of electrons. So how do we do this? So we have the standard potential or standard cell. Hydrogen is the standard cell. Hydrogen is set as 0 in terms of a reference cell. So we say that it essentially doesn't transfer energy. So we compare, so I've got this hydrogen cell and I'll connect a copper to it. And copper, because hydrogen is 0, whatever copper is, that's the value that gets written down in our little table here. So we have this little table. A couple of things. Everything you'll notice is written as a reduction. Okay, every single one of these is reduction. Reduction, reduction, reduction. All of these are reductions. So these are all what we call reduction potentials. Okay, so these are all reduction. Which of these prefer to be reduced? Okay, so the strength of the oxidizing agent, strength of the reducing agent. Don't think about it that way. Think about it this way. Think about the fact that lithium is group 1. Does lithium like to be oxidized or reduced? Does it like to be as +1 or 0? Does forcing it in this direction, is that a problem? Yeah, lithium doesn't want to turn into solid. It wants to be an ion. Okay, so lithium is negative because it doesn't want to go through this process. For this process, lithium turning into the metal, we have the reduction potential of -3.05. It hates doing this. So down here, if we have a negative charge, this is considered non-spontaneous. It really doesn't want to do that at all, right? So lithium is a terrible oxidizing agent because it doesn't want to oxidize, it wants to reduce, but it's an amazing reducing agent because it's happy to oxidize. Much like the other half here, fluorine is happily going to gain those charges. In fact, it's the most reactive thing on the periodic table. So this positive is saying that this is in fact spontaneous. It is a great oxidizing agent because it loves to be reduced. That's where that whole idea is backwards, right? So positive means it likes to happen, negative means it doesn't want to happen. That brings us to this idea of strengths of oxidizing versus reducing agents. There's 2 ways to do this. I want you to kind of ignore the thing at the top here. What I want you to do is when you do these calculations, ultimately this, and you can ignore this, we're going to come back to this and we're going to use it, but you can ignore that as well, almost. This is it. So whatever setup provides you with a positive E cell, that is the correct setup for a spontaneous cell or a voltaic cell. Otherwise, it's going to be a galvanic cell as written. Okay, so whichever one provides you a positive E cell. So let's take a look at a simple reaction here. The reaction of zinc with copper. So I have zinc 2 plus, 2 electrons for a spontaneous cell, meaning I need, so for this to be spontaneous, I need a positive E cell naught is equal to some positive value. So I need this to be positive, turning into zinc solid. Copper 2 plus 2 electrons is turning into copper solid. Again, these are both written as reduction. So the E naught reduction is equal to what? Well, let's look. So if we go back to this cell, we go back to this table, we see that zinc is negative 0.76 and copper is positive 0.34. So was it a negative 0.76 volts, positive 0.34 volts. Okay, so there's 2 ways that we can do this problem. All right, so that's all the information that we need. Let me just write this stuff down. An ox and a red cat. Okay. So the first one, and this is the one that I typically use, it kind of depends. I don't have to memorize any equations. I'm going to reverse the sign myself. Okay, so I have 2 reactions here. I have an oxidation, or I have 2 reductions. In order to have both of these in the cell, I can't have 2 reductions. One of those has to switch from oxidation to reduction. So looking at these 2 values, and we're just going to add them together at that point. If I change this to positive, so if I switch the direction of this reaction, okay, when I add those together, I'm going to have a positive value in the end. So I'm going to try this and let's see how it turns out. So I'm going to take reaction 1, I'm going to take zinc and I'm going to reverse the direction of it. So zinc solid turns into zinc 2 plus 2 electrons. And my E naught of oxidation, because I switched the direction of it, is now positive 0.76 volts. And I can just rewrite copper as is. So copper 2 plus 2 electrons yields copper solid. E naught reduction is equal to positive 0.34 volts. So when I add those 2 together, this is my E cell. It's the total oxidation reduction together gives me a total of 1.10 volts. It's positive. It is spontaneous. Okay. Well, what's at the anode? What's at the cathode? Oxidation, zinc, is occurring at the anode, and copper is occurring at the cathode. That's it. That's how we do it. That's reversing the sign myself. So I look at the sign and say, all right, I'm going to reverse the sign myself. The second option is to use the equation. E cell, if you want to memorize it, is equal to E cathode minus E anode. E cathode minus E anode, right? Again, this is going to be my reduction, and this is going to be my oxidation. Because we are not changing the sign here, the negative is already doing that for us. So the thing that's oxidized is going to have its sign switched anyway. Okay, and then we're just going to set it up. So what do I want at the cathode? Well, we want the positive one here, hopefully, minus the negative 0.76 volts. And when I add those 2 things together, I end up with a positive 1.10 volts. Again, that's spontaneous. So this right here is the thing that occurs at the cathode. And the 0.34 was the copper is at the cathode, and therefore the anode is going to be the other one, which is zinc. That's it. That's how we do determining what goes where when we're trying to make a voltaic. Next up, determine whether the following are spontaneous under these conditions. Again, it's the same exact thing. I can look and I can decide what's oxidized and what's reduced. We can do this, we can do this both ways, right? So step one is me reversing the sign myself. So what I have here are, let's see, let me just take the reactions actually. So I have copper going to copper 2 plus, and the 2 electrons plus 2 electrons. This is oxidation. So this is my oxidation half reaction. Okay. And we know that the E oxidation, again, if the reduction is equal to, and we already had this one, right? So negative 0.34 volts. Because it's already written, because that's the reaction, we know that copper is oxidizing. So we can say, all right, because it's oxidizing, it's negative 0.34 volts. Next up, sodium. Sodium plus turning into sodium solid. This is plus an electron. We can look this up. We know that this is actually going through reduction. This is going through the reduction half reaction. So I'm not reversing the sign of this one. So it should remain the same. So let's go look at our sodium up here. We see sodium is right here. So negative 2.71. So I'm actually going to plug that in. So negative 2.71 volts. I've already reversed the sign. So when I add these together, I'm going to have my E cell. E cell is equal to what? Negative 305. And this is non-spontaneous as written. So that was this. I reversed the sign myself. Again, if I wanted to do it, that's method one. If I wanted to do it the other way, using E cell naught is equal to E cathode, which is red cat, minus E anode, which is the oxidation half reaction. I know that the reduction was sodium. So sodium is negative 2.71 volts minus a positive 0.34, because remember, that's what the actual reduction potential for the for it was. So negative 2.7 minus that gives me, again, 3.05 volts. So either one gives me the same answer, essentially. All right, how about this next one? Plus. By the way, yeah, I should point out the fact that there is a problem with this one. Tell me what it, pause it and tell me if you can find me the problem with this, the next one. That's right, these are both oxidation. So let's just change this to 2 plus and this one to 3 plus. Sorry, they were both reduction, but yeah, so let's switch it to that, 2 plus to 3 plus. All right. So this is it. So that's pretty much what you have to do. So this is the last page. This is the most important, this is the most useful equation that we can actually have in like the entire set of chapters that we have. So take a look at this. We saw that there was a relationship between K and delta G last chapter through this delta G naught, or Gibbs free energy, is equal to minus RT natural log of K. Okay, so we should know all those. R is 8.314 joules per mole K. T is temperature in Kelvin. Okay, there we go. But there is a relationship that we have to check out now between E cell and natural log of K. We're going to see that below as well. But there is a relationship between E cell and equilibrium, as well as, because we know that once we're in equilibrium, we now have a dead battery, essentially, because it's no longer spontaneous or non-spontaneous, but it's non-spontaneous. It's neither right at that point, right? And we also have a relationship between spontaneity and delta G. So we have all of these links. I want to point out that the N is the moles of electrons. F is the Faraday constant. every single one of these is kind of under standard conditions. Okay, so and then we combine those together to get the E cell. So we saw that these two were linked. Now we're seeing that E cell and spontaneity is linked because that's what a voltaic cell is. So we can figure out the Gibbs free energy based on the E cell. And then finally, E cell is linked together between the two of them through that equation. Okay, so all of these are linked. This is, by the way, under standard conditions, they're 1 molar, right? 1 molar, 1 atmosphere. So same pressure and all that stuff. But under non-standard conditions, we have the Nernst equation. So this is under non-standard conditions. We are now at a Q. We were not at equilibrium. Okay, and I'm gonna skip actually writing out the derivation, and I'm just gonna write out the equation. E cell of the non-standard is equal to E cell naught. So that's me determining what the standard E cell is, and you can get that from any of these equations or doing one of these. Okay, E cell is equal to E cell naught. Actually, yeah, I'm gonna minus RT. Oh, sorry, not minus there. Minus RT NF natural log of Q. And actually, we can kind of take all of that and we can include it together because most of those are constants. E cell is equal to E naught cell minus 0.0591, because this is usually a standard temperature, over n moles of electrons, log of Q. Don't ask me why it changes. There we go. This equation right here is the Nernst equation. It tells you the standard, it tells you the non-standard conditions that we're at. Okay, so that's it. That tells E cell under non 1 molar concentration. And that is it. We're going to work on this in class.